Last time, we spent our time discussing buckets and heaps. And we developed this multi-level bucket structure, which we then sort of reinterpreted as a trie for holding integers in a small range, which we could access more efficiently than the sort of comparison-based heaps that we looked at previously. And so parameter-wise, we had this parameter delta. And at each level of the trie, each node has delta children. And we continue this for many levels. We'll have some number k of levels in the trie. And that means, so we have a trie of degree delta and depth k. And that means that the range of integers that we're able to cover in the trie is delta to the k power, right? So essentially, in our algorithms, we're arranging for that to be equal to c, which is the largest length of an edge, because we know that at any given time in our algorithm, we only really need to look at a range of c in values. So thinking some more about this trie, down at the bottom level, effectively, we're covering a range of c, right? And so what's the amount of space that this trie is going to occupy? How much memory do we have to allocate for all of these different nodes of the trie? It's order C, right? I mean, this is, it's like this is a delta array tree, but like a binary tree, all of the space is at the leaves. So the total space that we're going to be using is order C. And actually, it's very close to C, right? All of the levels above only contribute a 1 over delta additional factor. And so we talked about operations in this data structure. And insert and delete and decrease key are all done the same way, right? Because each integer that you might be storing just corresponds to a path in the trie. So when you want to insert something, you walk down the trie, and you put the item in all of the appropriate entries of the trie and store it down at the bottom. When you want to delete something, you go find it, and then you remove it from all of the layers of the trie, right? In this data structure, when you want to do a decrease key, that just means you do a delete followed by an insert, and you've accomplished your decrease key. The only one that's a little more, and so the runtimes for all of these operations are just order k, because you're doing a constant amount of work at each layer of the trie. The only one that's a little more complex is delete min. So what's involved in doing a delete min? So in keeping with the sort of versions of this that we've been using so far, we're going to assume that we have a current pointer to the minimum element, right? So we've got our current min. But when we want to do a delete min, take that out and point to the next one, what do we have to do? Good. So we have to go up the tree, right? Why do we have to go up the tree? And what are we looking for? Yeah, we're looking for sort of the next non-empty spot, right? So this is a generalization of the scanning that we looked at with Dial's algorithm, right? So we start at the bottom of the trie, and we're going to scan through the rest of this node of the trie to see if there's anything. If there's anything left, we will take it, right? And if there's not, we'll have to go up to the next level of the trie and scan until we find the first non-empty superblock, and then go down right, and start scanning through that block to find the smallest item, and then eventually, so the basic structure is we go up, and then over, and then down in order to find the next item. So what's the work involved in doing that?
Delta K.
What's that?
Delta K. Order delta K.
Delta K, right? So we're doing delta scan work at K levels for a total of order delta K. Is that clear? All right, we're going to do one, depending on exactly how you implement it, you may scan one block to discover that it's empty, and then you're also going to, at a particular level, scan through a non-empty block in order to find the first element so that you can descend to the next level according to to its pointer. Okay, so sorry, wrong page of notes. So if we set delta equal c to the 1 over k, according to our specification over here, then Dijkstra's algorithm using these operations is going to take us order, well, we're doing m decrease keys or inserts, and we're doing n of these delete mins. So k c to the 1 over k, right? So that's going to be the overall runtime. Yes?
Quick question. So when we're doing the scan for the delete min, we're going up, and do we actually have to scan each of the blocks that we're going up to? Since then we scan the block above it to see if that one's empty for the rest of it?
Well, so you can make going up relatively efficient. I mean, if you keep counts in the buckets, you can say, well, if I'm scanning this bucket, it's because I know it's not empty. If I'm scanning this layer, it's because I know it's not empty, and so I'm only going to do it once. But on your way down, you're going to need to scan each of the layers. Okay, but we'll come back to that. There's sort of some important insight there. But we sort of balanced this last time by choosing the right k. We got a running time of order m log base m over n of c. So that's where we kind of left off last time. Right? So picking up from there, I want to, so we've done bits. We did bits last time, but the time before that, we focused on this very important concept of being lazy. And so I want to assert that this particular approach using bits that we've taken over here is insufficiently lazy. We're doing too much work on our operations, and by procrastinating, we can actually reduce the total amount of work that we're doing. So can anybody identify sort of unnecessary work that gets done in this data structure, which often turns out to be work that we shouldn't have bothered doing? Yeah?
Updating the new min after an extractive operation?
Well, so updating the new min sort of at that high level, we are going to need to say what the next min is, right? We're going to be asked for the next min. So finding the min is not really something that we can avoid. You could imagine that we don't actually find the next min until we're asked for it, right? That we return the old min, but then we just sit there. But then we've just sort of deferred the finding the next min work, which is not a bad idea, until the next request. But we're still going to have to do the same thing of up, over, and down. So it's not on find min that we are doing unnecessary deferrable work. Yeah?
Even if there's only one leaf in a subtree, you still construct the whole chain of nodes. You could potentially think of a method that only saved the existence of that leaf in like somewhere higher in the tree.
Good. So yes, there is some waste in the sense that if our values are very spaced out, so that like they're each occupying a different leaf of the trie, then all of these sort of paths to the different leaves kind of separate very early on, and you're sort of wasting your time with many layers of the trie that all represent a single item. Right? And so really, once you just have a single item below your current spot, it's silly to have all of these extra layers. You could just store the one item that you've got. Okay? So that could actually be quite useful heuristic. However, there are going to be cases where the items that I care about are kind of bunched up, and I can arrange to have 2 in each of the layers. So that heuristic is not something I'm going to always be able to apply. This is great. I'm just sort of going up in a straight line. So you in the red hair, you're going to be next. Aloni?
Maybe when you're inserting, you're going all the way down and you're doing this long insert, and you don't really need, you can kind of insert it at the top or just keep a count, and then when you actually go into the bucket.
So this is a great insight, right? So when you insert an item in this data structure, you push it all the way down, right? Now, why might that be a waste of effort? Sort of taking that item and pushing it all the way down the trie. Yeah?
You might just delete it.
I might delete it. Well, there are no delete operations in the shortest path algorithm. But I might do a decreased key, right? So I do all of this work of pushing the item down one place in the trie. And then a decreased key happens, and I have to do all the work of pulling it out of that spot in the trie and putting it in somewhere else, right? And if that item is far away, right, I'm not going to need it yet. So why did I bother to so carefully place it? Okay, so this leads to a refinement by Dinardo and Fox from 1979. And so this was from the era when, like, you've all seen the glossy communications of the ACM, right? The sort of the trade magazine. So back in the 60s and 70s, communication of the ACM had articles like algorithm 317, shortest paths. Right? And it was very dry and just had these short little articles of, here's an algorithm. And so this was one of those algorithms. So the idea is, don't push down till you need details of exactly where an item is in the trie. So notionally, what we're going to do is we're going to have sort of the current min item. So we're going to have the trie, which is able to locate the smallest item in the trie. So here's our min. And the other items, as we get insert requests or decrease key requests, they're also going to go into the trie. But we're only going to push them down far enough to discover that they're not on this current path to the min. So, for example, from each of these top-level buckets, we're just going to have a bucket. We're just going to have it's literally going to be a bucket. We're going to store everything that is descended from this pointer in the trie in one great big bucket. Because right now, we don't care about the refined structure of what's in that bucket. Okay, and similarly for this and this. And we're going to do that at every level, that each non-empty entry at each level of the trie is just going to have a great big bucket of whatever belongs at that level. Okay, I guess at the bottom we won't need buckets anymore. We do still, because there can be ties. So really there are going to be buckets at the bottom level as well. Okay, so with this notion of just storing a bucket for each off-path entry at each level of the trie. Okay, so with that notion with that picture, we can really pretty much work out all of the details of this data structure. So how are we going to do an insert? All of you disdain to answer such an easy question. Yeah?
You can continue looking at the digits, base, whatever.
Yeah.
Until it's different from the minimum. And if it's different, then you put it into a bucket.
Great. So we're just going to push it down until it falls off the path. And then we're going to leave it in the bucket where it fell off the path, right? OK, So that's nice and lazy. We're only doing enough work to give us the resolution that we need right now. Okay. But this, of course, makes delete. What about decrease? Let's look at delete min first. There's something cool about decrease key, so save that one for last. What happens when we do a delete min? Yes?
When you go up to a parent and then scan, you're now going to find a bucket that has just a bunch of children, so you're going to have to recreate the tree that sits below it.
Great. So we still do the up and over part of the delete min to find the next non-empty entry. But now this non-empty entry, this is assuming, right, so the first thing you're going to do is finish scanning the bottom bucket, right, if the bottom layer. But once that empties, you're going to go up and over to find the next non-empty bucket. But now it's a bucket. So I've gone up over and I find this non-empty bucket. I don't have enough information yet to take the min out of that bucket, right? So I'm going to have to scan through all of the items in this bucket. Now, if I'm doing the work of scanning through all of the items in this bucket to find the min, what might I as well do at the same time? Yes?
Put that in the try and go down and
Expand that next layer of the try, right? So I'll expand the bucket to make the next layer of the try. And the nice thing is that this next layer is now on the current min path. Right? That's why I'm there. I'm there because because the min has taken me there. So it's right that I have expanded. So this maintains the invariant that all of the nodes on the current min path are expanded. Yes?
So there could be a problem if you insert something small in the min.
You are absolutely right. So this data structure, actually all of the data structures we've been talking about so far, all the way back to Dial's algorithm with its one giant array, rely on an important property of how the shortest path algorithm uses the heap, the priority queue. So what is special about the way a shortest path algorithm uses a priority queue that is not always the case for a priority queue? Right? You just sort of highlighted this problem. Do we have to worry about this problem in shortest paths?
Well, it could be a problem if you use a window. If you use a window to try or because you might really do research.
Oh, so you're worrying about the circularity. Let's sort of not think about sort of circular usage right now, but sort of if we're working with actual numbers. Yes?
We would have been at it already, right?
Exactly. So a key fact about shortest path algorithms is that they use their priority queues in a monotone fashion, which is to say that the value of the min in the priority queue is non-decreasing over time. Okay? And so anything that you ever insert into the priority queue is at least as large as the current min. Okay? And if you look back at all of the algorithms we talked about last time and that we're talking about right now, these all are implementations of monotone priority queues. They don't work for the general, or sorry, you can use things like them for the general case, but as I'm describing them, they are relying on this monotonicity property. All right, so delete min, we're going to do this sort of expansion process in order to figure out where the next min is. How are we going to evaluate the running time of this delete min operation?
Yes. You use the potential
function to S.
Ah, very good answer. That's always the right answer for data structures. But before you get there, why might we be thinking about invoking a potential function at all? Why can't we just say the runtime of this operation is X? Like, why can't we look at the real running time of this operation? Yes?
The number of elements in the bucket are different.
Great. So we have no a priori bound on the number of elements in the bucket that we're expanding, right? And so it may take us a tremendous amount of time to expand a particular bucket at a particular moment. And so we need, as usual, to move to a more amortized sort of analysis that says, well, it might take us a lot of time now, but over the course of the entire algorithm that we're running, these blips are going to average out, and we're going to be spending not too much time overall. Okay? So how do we argue that we're going to be spending not too much time overall? Well, as you say, a potential function is the right way to do it. I could phrase this in terms of a potential function, but in this particular case, I'm going to use a more elementary notion of amortization, where I just give each element in the queue some money to pay for the operations that we have to do on that element. So it's kind of a instead of talking about the potential of the entire system, I'm just going to look at the potential of each element and how the potential of that element is able to pay for the operations on that element. And in fact, I'm even going to sort of blur what is the exact potential function with the following simple observation. Note that any element only descends. Over the course of these insert and delete min operations, right? So I take a bucket, I expand it. So some of the elements, so I get child nodes, right? And buckets in some of those child nodes. So some of the elements that I've just scanned are now happy in their new buckets, and they stay where they are. But I may have to recursively expand the smallest child and expand the elements in those buckets down to the next layer. So each time I do an expansion, I'm pushing an element down to a lower level of the trie. Right? There's nothing that I do that brings an element to a higher level of the trie. Okay? So over the course of the entire algorithm, how much work am I going to be doing per element? Yeah?
Okay.
I'm going to be doing k work, right? Each time I do a scan on an element, the element drops by one layer. So in total, I'm going to involve an element in k scans over the course of the algorithm before it's at the bottom and is then removed by a delete min. So this drop implies that I'm going to do order k work per element. And so I'm actually going to, in an amortized sense, associate this work with the insert. So I'm going to call this I'm going to say that there's an insert cost of order k on an element, and that is going to pay forward for all of the scanning and descending that's going to happen when I unpack buckets. Yes?
You said we wouldn't use the potential function. Would we do something like set the potential equal to the size of all the buckets?
Yes, this is actually, well, the size of the buckets is not quite going to get at it because it actually matters what level the bucket is at. But here we would literally use a physics potential function, right? We say the potential of an item is equal to its height, right? And each time it goes down a layer, we recover a unit of potential, which pays for the scan work that dropped it by a layer. Okay? So yes, you can phrase this in a potential function. This is sort of the more sloppy and direct way. If you're not teaching and just writing a paper, you would probably say this. Okay? So this order k work can be charged at insert time and pays for all of the descending of elements. So what other work is there that we have to do that we're going to need to associate? Wait, this doesn't make the delete min free, right? There's still some work that we have to do besides this to find the min. What is that work? Yeah?
Scanning.
Exactly. So the work that remains is the scan work. But how much scan work? Do we have to, I mean, if we have to scan at every layer of the data structure, then we're going to be still paying delta times k, and we won't really have gained anything over the original data structure. Yeah?
But because of the algorithm, we know there's another item within C of where we are now. So that bounds how far we have to
So we can put an order C bound on the overall scanning, but that's still, C can be quite large, right? As we're moving into these multi-level buckets, we can handle quite large Cs, and so I'd like a better bound than that. Yeah?
So if at the beginning you didn't take the min all the way down, because down is good, then you know that in the level above, there's going to be a non-empty bucket.
Good. So if we could achieve that, if we could sort of ensure that, right, at each level we had, let's see, would that work? No, because if there's one item in the array, I'm still going to have to scan through the array in order to find that item. So that's something I'd have to worry about a little bit. Yes?
Give me k plus delta if you keep a count of how many things are in each level.
Good. So let's unpack that a little bit. So let's keep a count of how many items are in each of the buckets and each of the unpacked nodes that we're in. Okay. So if we do that, let's unpack delete. Oops, wrong board. Let's unpack delete min a little bit more. So on our delete min, we're going to keep counts. In nodes and in buckets. And what that allows us to do is we're still going to do the up, over, and down, like we talked about before, right? But now that we have counts, right, we know if, as we're going up, you know, OK, this node is empty because I've just removed the min, right? It had a count of 1. I've just taken out the min, so its count is 0. So I don't have to scan it anymore. I'll go up again, right? And so I go up until I find a layer where there is at least one more item. OK, so we go up till we find a non-empty node, right? And so this takes us k time, because we do constant work per level, right? Then in that non-empty node, we go over to the first non-empty entry. And how long does that take us? That's delta, right? And now comes the down. How much do we pay for the down? Right, well, we found this bucket, right? So we have these elements that have to be unpacked before we can go down, right? So how much do we pay for that? It's free, right? Why is it free? It's because we're using the insert potential, right? All of the descending that we're doing is coming along with unpacking of buckets. And we're already paid for the unpacking of those buckets. So we don't have to charge again for it. It's already covered. OK? And in fact, if we go back at this insert, right, this k for going up, I'm going to charge this to the insert also. Okay? As long as I charge it somewhere, I'm legit, right? So the summary now is that we have insert. Actually, let's sort of leave that and look at decrease key. So what's the cost for a decrease key? What do we have to do? So before getting to the cost, what's the algorithm for decreased key going to look like? Sorry, go ahead.
Well, you're going to have to, well, you're removing it and reinserting it. And so when you're removing it, you have to change the bucket number counts for the buckets that void. You only have to change it for the bucket that's in and anything above it.
Right. So essentially, we're going to be taking the item out of one bucket, right? So and then we're going to have to insert it in the new bucket. But if we look at that more carefully, we're going to see something quite nice. So where is that bucket? Remember, we have this chain of kind of current nodes that lead to the min, right? And now we have this item which is sitting in a bucket somewhere, right? So what's involved in the decreased key? We take it out of this bucket, and then what do we do? Yes?
So if it's small enough to go in the bucket of the minimum, then you scan all the way left.
Good. So if the item has become so small that it belongs in this entry of this node, then we push it down to the next layer. And what do we do at that point? Well, we figure out where does it belong in this node. And again, there's two possibilities. One is that it falls into some bucket of this node. The other is that it needs to continue down along the path of the min, right? So essentially, we're going to take it out of its current bucket, and we're going to start descending along the min path until the item falls off, and then we're going to put it into a bucket. So that's the decreased key algorithm, right? So we descend the min path until we fall off into a bucket. Okay, so now, how much is the cost of that operation?
Well,
yes.
Descending is paid for by the potential function.
Good, so the descent is free, right? Because we already paid for it with our potential. So what's left? Do we need to scan something? No, we don't actually have to scan anything. So what's the work? Yeah?
Well, we have to decrement the counts of a bunch of buckets going up.
How many buckets do we have to decrement counts for? I heard one right answer and one wrong. So they were both correct, but one of them was more precise. Okay. So it's less than k, but how many buckets do we have to change the counters for? Not quite one.
Two.
Two, right? It comes out of one bucket, it goes into another bucket. So we're changing 2 bucket counters, right? And that's all we're doing, right? So we decrement, we descend, we increment. We don't scan anything. So the cost of decreased key is order 1, right? Because the descent is free, because we already paid for it with our potential function. So, yes?
We paid for it in the potential function. Since it's not the same key, so we didn't pay for it.
Oh, no, but remember, what we paid for in the potential function was for each element to descend once through each level, right? And that was order k work in total. Okay? So that's the summary. Now we have an order k insert, an order delta delete min, and a constant time decrease key, which is a substantial improvement on what we had before. So now our Dijkstra algorithm is going to have a running time of, well, we do a linear number of decreased keys, but they're constant time, right? And we do n inserts and n delete mins for a cost of k plus c to the 1 over k. Okay. So that's our Dijkstra algorithm running time. Okay. And this is quite nice. If you balance for this, it turns out that you should set k equal to 2 log C over log C. And you get a runtime of order m plus n times log C over log C. So this is cool. I mean, you achieve log n's all the time in data structure, but this is sort of beating that log. It's sub-logarithmic now by a little bit. Okay. Great. And so, with quantities like this, you can start thinking about C's like 2 to the 64, right? I mean, this is not small constants anymore, right? This is a great data structure for integers. Forget about small integers, all right? Now, we do also need to think about the space, just to be a little bit careful. So how much space is occupied, right? We get a sort of a bonus in our laziness, because being lazy allows us to be lazy on space as well. So what's the space bound? Yeah?
Delta K.
It's delta K, right? We only unpack one node at each layer. So the space is order K delta, which from what we chose over there, it's order, C to the 1 over K times log C over, sorry, not C to the 1 over K. It's, I don't know, what is it? K is log C over log C, and delta, I don't remember what delta comes out to be. C to the log C over log C, so that's going to be about log C. So it looks like log C. So it's about log squared C or something like that. So that's a nice tiny bound for space. Plus n, of course, because you do have to keep the items around in the buckets. And we have n items to store. Okay? So that's great. Nice data structure, very practical, right? Just a few small arrays and some linked lists. And you're done. Okay? But you can go a little farther with this. So I'll just mention, I won't show you this algorithm, but I will mention that you can make some further improvement on it. This is actually a signpost of where we're going to go next. Let's think about the sort of basic operations that we were carrying out in order to support this data structure. So we had to do this sort of, going up to find the next non-empty node. And then we had this scan, right? We're supposed to scan across the node in order to find the next non-empty bucket. So what's really going on in that operation, right? So certain entries of this array are getting emptied or filled. So it's like we're activating and deactivating certain entries of the array. And then every once in a while, we want to scan across the array in order to find the first active entry, right? So if I set you that as a problem, what data structure would you use to solve it? Right? We've got a set of elements, and we keep needing to find the smallest one. A heap, right? So finding the next bucket is really kind of a priority queue problem. Okay? And so there's another opportunity for recursion. Okay? And we're going to explore that in a minute with Van Emde Boas queues. But first I'll mention that we have a paper by Cherkassky, Goldberg, and Silverstein about something called heap on top queues. Okay, which sort of said, well, if you've got a whole bunch of items that you're trying to keep track of, maybe you should just put them into a heap as your way of doing so. And it turns out that you can use this, and this is an unfortunate acronym because now they're hot queues. And we already used hot for heap ordered trees, but they called them hot queues. This is from 1997. This achieved a running time of order m plus n times log c to the 1/3 power. So a substantial improvement over the previous log C. Right? And I mean, in data structure terms, that's not facetious because everything in data structures is logarithmic. So logs are like your basic building block. And so going from log C to log C to the 1/3, that's like a cubic improvement in the parameter that you have hope of dealing with. So that's a substantial improvement. Okay. Other interesting story about these hot queues, or there's two reasons I wanted to bring this up. One is that this is a really nice example of an implementation study. So Goldberg does these all the time, where you take a data structure or you take an algorithm and you develop test cases for it, you study how it performs in practice, you think about things like the effect of the cache on the algorithm, you think about heuristics that might not affect the asymptotic running time but make a big difference in practice, and you report a lot of data about how this algorithm performs on test inputs, on real inputs, and so forth. So Andrew does this, I mean, he's done it for data structures, he does it for shortest path algorithms, he's done it for max flow, he's done it for min cost flow. Lately he's been working at Microsoft doing it for the shortest path algorithms that they use to sort of route in Bing on maps to give you driving directions and showing what works well in practice on that. So if any of you are thinking about doing an implementation study for your final project, this is a good exemplar paper to read to give you an idea about how to do it well. Okay. The other thing I thought worth mentioning about this is this guy Silverstein. He was actually, this was while I was at graduate school at Stanford, and Craig was several years behind me. Funny enough, he actually was my brother's roommate. And he was in the graduate program in computer science. And right after he wrote this paper, he dropped out of the graduate program to become the first employee at a startup company that was going just about then. And I still remember that my father, when my brother told him about this, my father sort of laid it into him at length about how it's really important to finish what you start, and you shouldn't be giving up in the middle, and so on and so forth. But it turned out that startup he joined was Google. He was employee number 1. And so now, the poor, he doesn't have to have a PhD, he doesn't have a PhD, and he just has to console himself with being a billionaire. And so I'm sure he thinks about, his lost opportunity often. Now he's actually working for Khan Academy doing the infrastructure for them. But anyway, so this is how, algorithms as your path to fame and glory. This is a nice story. So any questions about this Dinardo and Fox data structure before I go on? Yes?
How many buckets would we need at each level?
Well, so that's delta, right? The number of buckets at a level, you'll have 1 bucket per entry in a node. And so that's just our degree delta. So we'd have to go back and feed through our parameters, but I think it's about log C. Yes?
You only keep C, you can only hold C numbers. So would you have to include like a circular?
Good. So then there's this detail to fill in about for shortest paths, right? Where in shortest path the numbers go up to NC, right? They're not just C. So how do we deal with that? And there are a number of answers. The short one I'm going to give just in order to be able to move on is, you can have sort of your current C, and you can start preparing a priority queue for the next for the next C. And when you finally clear out everything, by basically putting everything there into one big bucket. And when you finish this collection of C, you start over with the next bunch of C. So at any particular time, you're only working with C stuff, and everything else is in a bucket to the side. Okay? All right. So before we abandon this whole priority queue study, I want to take us to one further place. And this is, again, riding on this idea that if you're going to have a, I should say that sort of what Cherkassky, Goldberg, and Silverstein did was the heap that they put on top of the buckets was just a standard binary heap. And this was a really good idea for practice, right? Because we know binary heaps work really well in practice. And so since they were concerned about implementation, using a standard binary heap was a good idea. However, in general, when you're thinking about the theory, you want to use the very best data structure that's available to solve a particular problem. So why should you use a binary heap when we've just done all of this work developing better heap data structures, right? So from a theoretician's perspective, it makes a lot more sense to use recursively the same data structure for the overall heap problem and for the problem of finding the smallest entry in one of the trie nodes. Okay? And so this idea was was explored a long time ago by Emde Boas. In 1977. So this is actually before Dinardo and Fox, before the sort of simpler story that I told you. And he developed what are now called Van Emde Boas queues. And I find Van Emde Boas queues very interesting to think about. They're not very complicated, but unless you define them exactly right, the analysis doesn't work. So I'm going to sort of, rather than kind of working it out a little bit at a time, just sort of state what is the Van Emde Boas queue data structure, and then we'll look at the running times. So we are trying to recursively build a queue. And the recursion that we're going to do now is not a sort of divide and conquer that we saw over here, where we divided the number into delta buckets. Instead, what we're going to do is actually split the bit representation of the number into a high half of the bits and a low half of the bits. So I'm going to describe for you a queue called capital Q, which is on b-bit integers. Okay. And it is a structure that contains, first of all, a field q.min, which holds the current minimum element in the queue. And it's an important implementation detail that this current min is not stored recursively in the queue. So we basically hold out the minimum element, and then we're going to recursively store every other element that's in the queue. How do we store those other elements? Well, we have an array, q, dot low, which is root u entries, sorry, where u, or where b is equal to the log of the size of the universe. So root u corresponds to b over 2 bits. Okay. So essentially, the way we're thinking of the Van Emde Boas queue is that it is a trie. But because of the way we're doing things recursively, the top level of the trie, which is able to handle numbers from 1 to u, is going to divide up the universe into intervals of size root u. Okay. So we've got root u different tries, or root u different substructures. We have an array of them. And so items, depending on where they are in this range, go into one of these structures. And each of these structures is going to store not the entire item, not the entire key, but just the low half bits of the key. And finally, we're going to have q.high. And so each of these entries is going to be a pointer to a b over 2 bit q, if there's anything in that entry of the node. And then finally, we have q.high, which is a Van Emde Boas queue on which of these subtries is non-empty. And so what that means is that it's on the high b over 2 bits of the integers. Okay. So this is a bit to take in. So let's sort of work it from bottom to top now. So in order to handle these integers in the range from 1 to u, which require b bits to represent, I divide them into root u regions, each of which has room for root u values. I use a, well, you could think of it as a bit vector to tell me which of these queues has anything in it. And I put those bits into a Van Emde Boas queue, which needs to be able to handle root u different values. So it is a Van Emde Boas queue on b over 2 bits, namely the high bits of the integers. Then, for each place where I have a non-empty sub-queue, I take all of the items in that sub-queue, but they all have the same high-order bits, so I don't really need to think about them anymore. Instead, I just insert the low-order bits, the low half bits of each entry, into the subtrie hanging off of that node, of that entry in the node. So is the structure clear? OK. So with that structure in mind, let's talk about the basic operations. So how do we do an insert into this Van Emde Boas queue? So let's say we want to insert x into Q. What's the first thing we have to check? Yes?
If it's less than the minimum.
OK, so if x is less than q dot min, then we're going to swap x and q dot min. Okay, in other words, we're going to put x into q dot min, and we're going to take the value of q dot min into x. Right? So now we've got an item that is not the minimum. And since it's not the minimum, it needs to be recursively stored in the substructures. So what do we do in order to recursively store it in the substructures? How do we figure out where it goes? Yeah?
I think you insert the high bits into the high structure and the low bits to the corresponding low structure.
Good. So that's roughly correct, but we have to think about the possibility of things being non-exist, about needing to create substructures that didn't exist. Okay, so first I'm going to write x as x high and x low, where here we have the high b over 2 bits. And here we have the low b over 2 bits. Okay. And so now I have some cases to think about. Okay, so where do I look for where this item is going to go? Yeah?
You can check if q dot high is empty.
Good. So if q dot high, now q dot high is an array, so I need an index in order to avoid having a type error. So what's the index? Right. So I use the high bits to index into the q dot high array in order to find the right subqueue for this item. Okay. Now there are two possibilities, right? The easy possibility is that there's already a queue at q dot high, indexed by xh. If that's the case, what do I do? Well, then I insert sorry, this is not q dot high, this is q dot low of xh, right? So then I want to insert xl into q dot low indexed by the high bits. On the other hand, it's possible that q dot low at xh was empty. There wasn't anything there. What do I do in that case? Yeah?
Create one of those.
Good. So otherwise, I have to create an empty q dot low of xh and insert xl in it. But then there's something else that's important for me to do. So if I've just created an empty queue where there was previously no q, I have to remember that. What do I have to do in order to remember that? So that I can find it later at the right time. Yes? Right, so I have to update q.high. And what does that mean, update q.high? What do I have to put into q.high? I have to put that index of this new q, which is x.h, x high. So I have to insert x high into q.high. Right? All right. Now, I know it's bad practice, but just in order to keep things close together, and since I'm only going to need 2 boards to finish Van Emde Boas queues, I'm going to use the middle 2 boards instead of going back to the left. So what do we do about delete min? So what are my steps in deleting the min? Obviously, the first thing I have to do is find the min. Where is it? OK, so misusing programming languages, I will immediately say return q.h, q.min, but not yet. OK, wouldn't it be nice if you could program like that? I often want to do exactly that in my programming, right? So what do I have to do before I return q.min? Well, I already found it. It is q.min. I have to repopulate q.min, right? So how do I go about that? So to replace q.min, how do I figure out where the next min is? Yeah?
So in qlow, you find the entry, the smallest entry that's populated. And then
OK, so the idea is we're going to find the smallest entry that's populated in the array q.low. But you're making an assumption there. What are you assuming? You're going to get a seg fault if you code that way. Yeah?
Q.low still has entries left there?
Right. You're assuming that there's something there. We have to worry about the possibility that this queue only had 1 item in it, which was at q.min, and everything else is empty. So how do we check for that? How do we check if there's anything else in the queue? Well, that's a question we can ask by saying, let's look in q.high.min. All right, so remember, q.high is the queue on the high order bits of everything that came in. And so if there is a next number, there's going to be a min in q.high.min. Okay? And so if this is null, then the whole queue is empty. So set q.min equal to null. Now, if it's not null, we can proceed as you suggested. We need to find the smallest item remaining. So if there is a smallest item remaining, it's going to be pointed at. Q.high.min is going to tell us where it is, which queue it's in, right? So in that case, we're going to look in let me put it this way. It's going to give the first non-empty bucket index, which we'll call xh. And so that tells us that we should look in q.low of xh. Right? And so what should we do with what we find there? Yeah? We're going to do a delete min from it. And let's call xl what comes back. We're going to do a delete min from q.low of xh. Right? And what's going to happen, we have to do some cases now when we do this delete min. So what might happen when we do a delete min from q.low of xh? Yeah?
Well, it might become empty.
It might become empty. So we have to say if q.low of xh is now empty, what do we need to do? Yeah? Right. If it's become an empty queue, we want to erase it. Right? We don't want to be distracted by it later. So we're going to want to do a delete min, or we're going to want to delete this value xh from q.high. Okay. And you'll notice that this is a delete min operation. Right? And so now our answer that we're returning is this number xh concatenated with xl. So this is what we're actually going to return from our Emde Boas queue. So it remains to analyze the runtime.
Human, right?
Sorry? Sorry, yes. Thank you. That's not the thing that we return. It is what we store it's what we store in q.min. Which has now been repopulated. Yes?
You need to run the delete min on q.h or q.high.
Sorry, did I? So q.low of xh became empty, so we need to remove xh from the set of high order bits that we are that we're currently storing, so that we don't find it later.
Well, like before we look at q.high min, don't we have to delete min on q.high?
Isn't that what we're doing?
Well, it's not written in there. Like before the look stage.
Let's see. Let's look at this more carefully. So I do a delete min from q.low of xh in order to. So at the beginning of the delete min, so all of this work that I'm doing here is simply to figure out what goes into q.min. What new thing goes into q.min, right? So I need to find the min of what's in all of the sub-data structures.
So q.high.min, you already know that because it's the first component of q.min.
That's right.
So you need to actually delete min on q.high first, and then look at the new q.high.min that comes from that.
No, because it might not change, right? So q.high.min might not be changed by this operation. So I don't want to start by doing a delete min, right? If in particular, if q.low of xh does not become empty, right, then xh is still the minimum value in the subsidiary queues, and so I want to keep that value xh where it was.
So the only case you get if null that line is if the original q.min is null.
That's right. Okay. So let's look at the running times now. Okay. And let's start with insert, because it's simpler. Okay. So if you just look sloppily at this runtime, there's sort of a simple and natural recurrence that you would write down for the runtime, right? You would say that, well, in order to do an insert of a b-bit word, right, basically, if I look at this, I do an insert of the high bits, and I do an insert in the low bits. So the kind of running time I should be expecting, and I'm going to put a question mark here, is that it's 2t of b over 2. Right? One insert in the high order queue, one insert in the low order queue. So what would that resolve to as a runtime? So that would give me an order b running time. Okay? Which is kind of nice. It sort of says you're linear in the number of bits, which is still logarithmic in the value of the integer. But actually, it's much better than that. So what can we say about these two recursive calls? So we've got these two cases that we're thinking about, right? either the low order queue, the first queue we look at is non-empty, and then we do an insert into q.low. The only time when we do two recursive calls is when q.low was empty, and then we have to insert into the new queue that we create, and we also have to insert into q high. But I claim that this is actually a nice pair of inserts, that it's not 2t of b over 2. How come? Right, so there are two inserts here, but I don't need to tar them both with a t of b over 2. Yeah?
If you wanted to insert it into an empty queue, you can just set it to be.
Great. So the key is that one of our two inserts is into an empty queue. Right? And inserting into an empty queue is very fast. You just need to create a queue with one item. So that takes a constant amount of time. So in fact, the running time for insert is t of b over 2 plus order 1. And that means that our overall runtime is log b, which, just to make the point clear, is log u. Sorry, I switched to u when I was previously using c, right? But this is the size of the range of numbers. So instead of being polynomial in log of the integer, we're now logarithmic in log of the integer. So we've just achieved an exponential improvement over the previous data structures. OK? Question? No. All right. The analysis for delete is exactly the same, for delete min rather, that if you trace through the code, you may see yourself making two recursive calls to delete. However, if you're making two recursive calls to delete, one of them is on a trivial data structure that only has one item in it, and that therefore takes constant time. So delete min also takes log u time. Okay, and so the Van Emde Boas priority queue is the best that we know of for these sort of priority queue operations. And in fact, as you will show in your homework this week, the Van Emde Boas priority queue is not only a priority queue. It's actually a whole search tree. So you can use the Van Emde Boas tree as a search tree. You can insert, delete, not just delete min, but delete, and find things all in log u time. Okay? And you'll work out the details of that in your homework. Okay? And so this is useful. So for example, you can use this to sort n items in n log u time instead of in n log n time. It does have a drawback or a problem, which is space. So what's the space usage for a Van Emde Boas priority queue? In fact, I don't even care about the recursive part of the structure. What's the space usage at the top level? I don't have a D, I don't think.
D or U.
So it's not quite as bad as U. I don't keep an array of size U around. But it's square root of U. That's a little bit scary. Right? If you imagine, again, the Van Emde Boas priority queue seems really attractive for the kinds of data structures that we're doing right now. If you want to do some cracking of SHA-1 codes or something, and you're storing a lot of integers. But if you're trying to work with 128-bit integers, then you need to use your whole machine just to store a lot more than your whole machine, just to store the priority queue. So that's bad. So how might we get around that problem? Yes?
That also gives a question of the runtime, because array we are assuming array access is not auto-run.
Yes.
Really, you have to add the pointer.
Good. So there's a little worry here. If you're going to make an array of size square root of u, do you have to initialize it? Right? If you have to initialize your array of size root u, then you're going to be spending root u time, which is probably more than all the time you're going to spend accessing the data structure. Right? So that's a problem. Now, it turns out there's a clever trick you can play to simulate an array initialization in constant time without actually writing into the array. Okay? And maybe I'll put that on a homework, or maybe I'll let you think about it. But essentially, you need to use a little bit of extra space by a constant factor, and you can simulate the effect of having an initialized array, of being able to initialize the array actually whenever you like in constant time. So that does away with that particular problem. But we still have this problem of just having the space. And if U is large, we won't have the space. So how might we address that problem? This leads very nicely into the next topic that we're going to cover. Yes?
Can I just sparsify the array?
Good. So we've got, if you think about it, it's a very sparse array, right? We're storing a very small number of items into a very large range of possible values. Has anybody seen a data structure that's sort of optimized for that sort of problem, where you just want to be able to, look up by a particular index or key an item and then get it back and not use too much space to store everything? Yeah?
Store sparse matrices.
You could use this trick to store sparse matrices, but in fact, you can use it to store anything sparse. Hash tables, right? So in practice, if you were ever so crazy as to implement a Emde Boas queue, you would use a hash table. And from a practical perspective, this solves the problem, right? We do hashing. Now, instead of using root uspace, we just use n space in order to store n items, and we're all done. It actually creates some problems from a complexity theoretic perspective, because if you're really thinking about log u's, you need to think about the time it takes to implement a hash table. Okay? And so what we're going to see in this class is that you can implement a hash table so that that does accesses in order 1 expected time. So we're going to start playing with randomized algorithms, which have a probability distribution on their running times. But we're going to be able to achieve an expected access time of order 1 on our hash tables, which is all you need in order to then implement your Emde Boas priority queue. If, on the other hand, you want to have a deterministic algorithm, then you need to use a little bit of extra space. You can't do it in n space, but I think you can do it in like n to the 1 plus epsilon space deterministically with order 1 accesses. So either you do randomization and get exactly the space that you want, or you sacrifice a little bit in space and use a deterministic hash table, and in doing so, still get the log u time bound. But you do have to move on to hash tables, and that, of course, makes the data structure much more complicated, that you've got this whole hash table, whereas intuitively, you just wanted to think about an array. All right? So questions about that? All right. Then let me introduce you this class to hash tables, and then we'll spend part of next class looking them over. And many of you may have seen hashing, but I think it's important to cover because it lets me introduce you to some of the fundamental notions of randomized algorithms and how you analyze randomized algorithms. And when I finish teaching you about hash table, I will have also showed you everything that you need to know about probability in order to get through this class and most of randomized algorithms. So let me actually list those things so that you can study them for next time if you don't already know them. So all you need to know about probability for this class are linearity of expectation, indicator variables, independence, the product rule for probabilities, and the Markov inequality for bounding the probabilities of certain events. Okay. So just to describe what hashing is. Hashing is a tool that we use for the dictionary problem. Okay. Where we want to be able to support insert, delete, and find. So this is what we use display trees for, right? Binary search trees can certainly be used to solve the dictionary problem. But binary search trees are comparison-based. And hash tables, like the queues that we were just looking at, leverage the fact that often the things that you are trying to manage are integers. Okay? So we are going to look at the sort of version where the keys, the things that you want to insert and delete, are integers that fit in a machine word. And we're going to ask how we can do better than a comparison-based binary search tree in order to do this. And so we're going to leverage the same ideas as we did in priority queues of being able to do indirect addressing, of being able to use the value of a key to index into an array. And in fact, we're also going to use now arithmetic. We're going to start multiplying keys by other numbers, all right, which is something that you can only do by treating them as integers. So if I'm in this world where I have integers as my keys, what's the most obvious way to store a dictionary? The simplest data structure for storing a set of integers. An array, right? So k goes to entry k in the array. Now, what's the problem with that? We've just been discussing it. It's the problem of space, right? So if your keys are all integers that fit in a machine word, they're 64-bit integers, well, you don't really want to have to make an array of size 2 to the 64 in order to store all of those keys. So the obvious idea that you invoke is to put k into an array entry at h of k, where h is a hash function that maps the range of values from 1 through m, which will be my universe, into a range of values from 1 to s, where s is much smaller than m. Okay, so now instead of using the actual value of the key, I compute some function that makes a smaller number, and I put the key into that smaller number. Now, what's the problem with hashing to a smaller number? Collisions, right? Maybe h of x equals h of y, and x and y both want to go to the same place. So what do I do about that? Well, there are a few obvious solutions, but the one we've been using so far is make buckets. Right? So I could just have a linked list at h of x for all of the items that hash to that position. So that solves the problem of collisions, but it introduces a new problem. So what's the downside of putting a linked list off of a particular entry in the array? Yeah? Now it's going to take you a time to look up, right? The really nice thing about an array is you index into the entry and you look and there's your answer. But if now there's a linked list hanging off of each entry in the array, I'm going to have to walk through that linked list looking for the item the specific item that I'm looking for. So right now the access time becomes proportional to the number of items in a bucket. Okay. So that sort of defines the core problem for hashing. So the goal is to find a nice hash function that puts only a few items in each bucket. But that also has a problem. Okay. There's a problem with any function that I might use that I hope to put a few items in one bucket. So what's the problem?
So basically, an adversary can just like put
lot of items in the same bucket.
Great. So the problem is that for any particular hash function, there exists a bad set of keys, right? So, you know, with the numbers that I picked up here, right? So if I said I'm hashing from 1 through m to 1 through s, so, you know, I have an array of size s. I should be able to put s items into the array, all into different places so that they don't collide with each other, right? But for any hash function I pick, there are certainly going to be a bunch of items that all have the same value for the hash function, and therefore all end up in the same place. And so if I'm unfortunate and all of the items that are inserted have the same value on the hash function, then even though I'm using a hash function, or because I'm using a hash function, I still get all of these collisions and the access time is bad. So for any particular hash function, there's a bad set of keys. And that means I can't pick a hash function that works. So we're going to back off on our goal. And we're going to seek a family of hash functions such that one of them is always good for us. OK? And so that's the problem that we're going to tackle on Monday. Remember, Friday is a holiday. So on Monday, we will pick this up and ask, how do we construct a family of hash functions so that we can always hash any particular set of items well? All right? So just a reminder that you should have turned in the first problem set. I think grading has been worked out, or is being worked out, and we are going to post problem set 2 this afternoon. We need almost graders. Is everybody holding back because they might drop the class? Remember, you're going to have to grade at some point, and actually, as we go forward in the semester, we're going to reduce the number of graders that we have per week. So you'll probably end up doing less work this week than you will in the future.